for the group work problems. Okay.
I can start.
Go ahead.
Yeah,
Okay, so I think pretty much all the questions were about the same. And so the first one talks about a population of plants that has 396 red flowered and 557 white. And it wanted to know what the allele frequencies were for the dominant and recessive. And so all you have to do for the first one, for the recessive, is you take the 396 over the total, and then you get a frequency of 0.645 or 64.5%.
Mm-hmm.
You guys get that?
Yeah,
Sure.
you also have to square root that to get that first.
Yeah. Sorry.
Yeah, 396 divided by 953 is like 0.4155, something like that.
Yeah, and then you square that, and then you subtract that from 1 to get the value of the other one.
Mm-hmm. P.
Yep.
Yeah, sorry, of the other one. Mm-hmm.
Yeah. Okay. Let's see, and then there was for B, it wants to know the genotype frequencies for homozygous, heterozygous, and then homozygous recessive.
Mm-hmm.
And so for the homozygous dominant, we took I took the 0.355 and multiplied that by 2, and then I got the 0.126 or 12.6%.
You mean you squared it?
Yeah.
Okay.
Sorry.
That's fine.
Yeah. Okay, do one of you guys want to do the next one?
For the heterozygous?
Yeah.
Sure. So for that one, you write from the equation p squared plus 2pq plus q squared, where each one represents the homozygous recessive, homozygous dominant, and the heterozygous. The heterozygous would be the 2pq, or where it's 2 times the frequency of the one allele times by the frequency of the other allele. So it'd be 2 times 0.355 times 0.645, which I got about 0.458 or 45.8%.
Yep.
Mm-hmm.
Yeah.
And for the homozygous recessive, just took q squared, which is 0.645 squared, which is 0.416. About. So yeah.
Yeah.
And then I could do the next one as well. So the expected number of heterozygous individuals in this population, so with the whole population in this one that we're measuring is, or looking at, is 953 total. So we just multiply that by the 0.458, get approximately about 436 individuals.
I rounded up for that because I always round up.
Yeah. So I have a question about that, because I remember my biology teacher when I took 181. Like, we're not supposed to round down or something. If it's like 436.1, we round to 437. Isn't that true?
Yeah, that's what I thought too. That's why I
Right,
said
but the key said 436.
Yeah, I don't know. See, here's the thing, Joachim. I was told that in my biostats class, but in my bio 181 class, they just followed the normal rules of rounding.
Okay, because my biology 181 teacher, he said that if there's like a small fraction of a number, you still round it up.
Because you can't have like a quarter of a person.
Right.
Yeah.
And if you go down, then you're neglecting that quarter of a person.
Mm-hmm.
So, yeah.
I know, that poor arm or leg that's not included.
I mean, for the sake of the assignment, I don't think it really matters, but, like, since the key didn't really pay attention to that, but I don't know. Like, maybe we should ask her.
Okay. And then I had a question about the Hardy-Weinberg equation, or equilibrium.
Mm-hmm.
So that's basically saying that populations are going to stay the same without evolutionary factors, but that's also not really possible, right?
No.
Like you're
Yeah,
always going to have.
I don't think it ever exists.
Yeah,
like,
so
ever.
this is just a theoretical thing that can't actually
Right.
happen.
But the thing they use it for is to pull out the null hypothesis.
Mm-hmm.
And what they can do with that is measure what kinds of, like, how evolution occurs, if that makes sense.
Yeah.
So it is useful, but like in reality, does it work? No. But we can see, like, okay, that evolution has occurred here, and then we can look like, oh, what has happened, or something like that.
Okay.
Yeah.
Just trying to figure out how it's happening.
Yeah.
Yeah. Well, it talks about 5 different kind of, I guess, parameters, if you will, that make it into disequilibrium, you know? Like mutations, natural selection, migration, non-random mating, and what was the 5th one? The 5th one was like... Anyway, yeah, there are like 5 parameters, you know, that if any of them are occurring, then it's in disequilibrium.
Right.
Yeah.
And
Yeah.
so, actually, so I was kind of talking to Joachim a little bit about this. So with the chi-squared thing, we're supposed to have...
Which question is that, by the way?
that's 5b. You know,
Okay.
we're supposed to come up with a chi-squared value and then see, you know, interpret it, whether to reject it or fail to reject it, you know, all that stuff.
Okay.
So I'm trying to figure out what is supposed to be the expected frequencies. I looked on the notes on the PowerPoint, and it said that the allele frequencies are constant or do not change. So I assumed that meant that the allele frequencies are like, you know, if you have two alleles, that it's half and half, you know? So that's what I used for my null hypothesis, you know. I took frequencies, I calculated the number of individuals, and then I compared it to the observed rates and came up with the value. But I was apparently way off because I checked the key and my answer was way off. So I don't know. What did you guys do?
So what did you get for your expected value first for those?
Sure. So I said the expected frequencies were m is equal to 0.5 and n is equal to 0.5. You know, it's half and half. Then for each, so homozygous recessive and homozygous dominant, I got 0.25, and then heterozygous, I got 0.5. Then I multiplied that to the total number of individuals, which was like 200. You know, so you know you get about 50 mm to 100 mn to a 50 nn ratio. Like that would be the expected ratio.
So I have
And then I use that as my expected.
Did you watch the video she put up?
Yeah, I did. So
that like
was there
went
a video
through this problem? Huh?
Was there a particular video that they talked about that?
Yes, there was.
Damn.
For this problem. So first, what I did, so like I looked through it, and you have like 168 MMs, 30 MMs, and then 2 NN, right? And so there's 200 individuals. Now you want to first like calculate like all the alleles. So you have 400 total alleles, right? So M, that's 2 times 168 plus 30. And if you divide all those by 400, you get 0.915. And then N, that's 4, like 2 times 2 plus 30 divided by 400, and that's 0.085.
Yeah, that's what I got. I got that.
Okay. And the null hypothesis then is that the population is in Hardy-Weinberg equilibrium. So
what does that mean? Like numerically, though?
That means that, okay, the null hypothesis is that no evolution is occurring, like, if that makes sense, I guess.
It does, but like, what does that mean in terms of like M and N frequency?
Well, you can see that, like, if there is, let's say, for example, that there is a lot of migration in one area and emigration, that's gonna mess it up quite a bit, probably. Like, if that happens, that's gonna take out the frequencies and make the allele frequencies. They're gonna like make those numbers deviate a lot more than if it doesn't occur.
Or especially like with the bottleneck effect that we learned about a lot in like 181.
Mm-hmm.
So like that's what happened with cheetahs, and that's why they have such a hard time with them, because when so many of them got wiped out, you had too many with similar genetic traits, which is why there's a lot of health issues in the existing ones. And so with that, like with the MN, you can get
genetic drift.
Proportionate ratio, yeah.
Was when they refer to like genetic drift, but like anyway, I don't remember that. But going back to this problem though, so M was 0.915 and N 0.085. So P squared. So if we square both of those, we get our P squared. Okay.
Mm-hmm.
So 0.8372 and 0.0072.
Mm-hmm.
And if we multiply those by 200, we get our expected value.
That's supposed to be the expected?
Yes.
I thought those were the observed.
So the expected becomes 167.44. And the expected becomes 1.44 for the NN. In the video, she wrote MN for 1.44, but that's obviously not correct because she switched them. And MN was 31.12. And the observed is just what we got, so 168, 2, and 30.
Okay.
Does that make sense?
Sure.
Yeah.
Okay. And now you plug the numbers into the chi-square equation. And that gave me like 0.25967.
And then you interpret it, and it should be you fail to reject it, right?
Right.
Yeah.
Okay.
So in this case, it's in Hardy-Weinberg equilibrium then.
Okay.
But I see so how does that become the expected? Is that kind of what you mean with your question then, or?
Well, I mean, the thing that confuses me is that so the M frequency 0.915 and the N frequency 0.085, we derived those from the observed values that she gave us in the problem, right?
Right.
So how does that become the expected? Isn't that supposed to be the observed?
Yeah, that's what I'm. Yeah, because I agree with you. That's kind of confusing. That we are observing. We're taking our numbers from the observed and creating the expected value.
Yeah, because we're assuming that this is. I mean, I know the null hypothesis is that we assume that it's an Hardy-Weinberg equilibrium, but if we use the observed values and say they're expected, then why do the chi-square test ever? Like we're just basically saying it's an Hardy-Weinberg equilibrium every single time.
I agree with you.
Yeah. I don't know.
That makes sense what you're saying.
I mean, I'll have to go watch the videos again to find out how she did it. Maybe she offers an explanation on the videos, or whoever did the videos, on why those become the expected values. It doesn't really make much sense to me, though.
Yeah.
Well, that was the only one I had a question on. The others, I've got. Sometimes she didn't round the decimal place to what I rounded it to, so our answers were slightly off, but whatever.
Right. Yeah. Yeah. I actually wonder about that too.
Where we should round.
No, with the expected value.
Oh, yeah, that was the thing that really confused me.
But
Like I said,
the
I
thing-
looked on the PowerPoint, and it's.
What did we do? Like, was it 2 lessons ago, 3 lessons ago when we had those problems? How did we find the expected value at that point?
Well, we would create our own null hypothesis that we thought described the general trend of what we saw in the observed values, and then we would calculate from the total. Like, for example, if I said the null hypothesis is, oh, this follows a Mendelian inheritance, so therefore it should be a 9:3 to 3:1 ratio,
Mm-hmm.
or a dihybrid cross or whatever, and then we would use that and calculate what the expected result should be,
Right.
and then we compared it to the observed. That's how we did it
Yeah.
before. Which,
And then we would
honestly,
just look at what they actually gave us and compare.
Which,
Okay.
honestly, I did that on the exam, guys, and I still got it wrong, so I'm getting a little annoyed with this guy squared. Crap.
But if that's the null hypothesis, that it follow Hardy-Weinberg, wouldn't that kind of create the same thing? Like, so my question is, could I put in, like, make any kind of numbers there, and would it always follow? Like, if I always derived it from my own numbers, will I always? Do you get
Well,
what I'm saying?
Because it has to be whatever Hardy-Weinberg would be, and can we just know that? Can we just make that up?
I don't know. That's the thing, because I'm wondering, like, if we're deriving from our own numbers and making it look like this, will it always yield so that we fail to reject it? Does that
I
make
mean,
sense? Like,
yeah,
mathematically
kind of.
speaking.
I know it's kind of really dumb. It would be like if I made hot chocolate that scalds your tongue, and I say hot chocolate always scalds your tongue. See, look, I had this hot chocolate. It burned my tongue. Therefore, all burned my tongue. So you know what I mean? Like, it's kind of stupid.
Yeah, but like what I'm saying here is that if we derive it from our own numbers that we start with, will it ever violate the Hardy-Weinberg equilibrium, or like will it be in disequilibrium?
I don't think so.
Yeah.
Here, guys, tell me how you calculated your chi-squared. Like, tell me the math that you did.
Well, 168 minus 167.44, squared it, divided by 167.44, and then 2 minus 1.44 squared divided by 1.44 plus 31.12 minus 30 squared divided by 31.
Okay,
Well,
so you took 200 times by 0.915 basically, and then that was your expected.
what?
You took sorry. So to get the first part, you said it was like 168 minus by 167.44. Is that right?
Yeah.
Yeah. You got the 167.44 by multiplying 200 by 0.915, right?
No, 0.8372.
8372.
Yeah.
Let's see.
And
Yeah.
that's
Sorry.
0.915 squared.
Right. It's 0.915 squared. Okay. Yep. Okay. Mm-hmm.
Yeah.
I don't think we would ever reject the null hypothesis if we did it that way.
You think it would always follow it?
Mm-hmm.
I mean, you could try it. Put your own numbers.
Throw me a number, man. Throw me a number, and I bet you that it won't.
All right. Want to try it real quick?
Sure, I can do it.
All
Go
right.
ahead, throw me some numbers, and
Well, let's use 200. And let's have 130 mm's. And then we can do 35 mn. And 35 nn.
Okay.
Okay?
Okay.
Sorry, what was the observed value that you said?
130 mm, 35 mn, and 35 nn.
Okay.
Okay, so for the M frequency, I got 0.7375.
Yep.
And 0.262 for the N frequency. We take 200.
What did you get for n?
For N, I got 0.2625.
Yep.
Okay, and then we'll
Square
Square
those.
multiply by 200. About 108.7. And there's a bigger gap than before.
So the expected, did you get 108.78?
Yeah.
But that is clearly gonna
Fail to reject. Reject. I mean.
reject it. Yeah.
Yeah. Oh, I guess there are circumstances. Okay, never mind. I'm wrong.
Well, that's good to know.
Yeah, that is good
Okay.
to know. Okay, fair enough.
Yeah, I don't think we have to go further than this.
Okay. Yeah. Okay, I could see it. All right. So, weird.
But why?
Just like when you think about it, though, it just doesn't make sense, though.
Mm-hmm.
I think I need to rewatch those videos because I'm still a little confused about this.
Yeah, same here.
Well,
Maybe we should ask her.
how about this, guys? So even though we derive the M and N frequencies from the
Mhm.
numbers that we have, and we kind of use that as like our expected frequencies, that doesn't necessarily mean that we're going to have the same homozygous dominant, homozygous recessive, and heterozygous numbers. Does that make sense?
Yeah.
Wait, say that again?
So we're talking about the allele frequencies for M and N, right? Like
Right.
those,
Yeah.
but it doesn't say anything about like how many homozygous recessive, how many homozygous dominant, or how many heterozygous could come from. Because you could have like 180 of MM and then only have like 10 of MN. Does that make sense?
Well, the expected here is 108.78 that we got was for MM.
Mm-hmm. So, I mean, kind of the point that I'm trying to come to is, so you have your M and N frequencies, which are whatever, pick a number, but we don't know what those M and N's go into. Does that make sense? Like,
Mhm.
for the M, most of them could go into heterozygotes, or most of the N's could go into homozygous recessive. Does that make sense?
Yeah.
So even though we derive the frequencies from the observed values, that doesn't necessarily mean that we're going to have the same heterozygous, homozygous, recessive.
Oh. I think I see what
numbers. Does that make sense?
Mm-hmm.
Does that make sense, Natalie, what I'm trying to say?
Yeah. Yeah, it makes sense. It's just also confusing me more. Like, I understand what you're saying. I have to consider a lot more when I'm doing these problems.
Yeah. So I have a suggestion. What about we send her an email?
Okay.
Would someone want to do that?
So what are the questions exactly that we need to ask?
Why, like, how? So like we're deriving from our observed value. We're deriving the expected value. Like, how does that? How can we get a chi-square out of that? Like,
Okay.
I'm not exactly sure how to formulate it.
How do we get a chi-square when deriving the expected value?
Yeah, like
Or how
like
do
we did here.
the chi-square?
We saw that it doesn't always follow the Hardy-Weinberg equation, but like we're kind of confused. But whoever sends the email, make all three of us and the teacher included in the email so we all can see the answer.
Okay. I can send the email if you guys like.
You
yeah,
can?
that'd be fine.
Okay.
Okay.
I can go ahead
and you have our emails?
Yeah, I have all your emails.
Okay.
So
Okay.
yeah, so basically, Natalie, what we're trying to ask is, so in part A of problem 5, we derived the m and n frequencies from the observed values that she gave us in the problem, right?
Yeah.
Joachim and I are wondering if you're deriving the frequencies, the allele frequencies, from observed values, wouldn't the chi-squared value always say that it's an equilibrium? You know what I mean? Because you have observed minus expected, right? And you're basically saying you're saying the expected is from the
observed.
Is from the observed that you got, you know. So that's basically what we're confused about.
Yeah, no, I understand why you're confused. Okay. Is that everything for today?
So I mean, go ahead.
Huh? No, yeah, I think so.
Okay.
Yeah.
Sorry.
The other 4 problems I didn't have any problems on.
Yeah, they all. I mean, this stuff was a lot easier for me than last week was.
Yeah, there was just one thing that kind of did confuse me a little bit. That was the one that was autosomal with dominant with the dwarf, that you had to put the recessive as the q squared. Yeah. But I figured it out after a while. But
which problem is that, Joachim?
3. So you have to set q squared equals 24,999 over 25,000. And then do it that way. Because I tried the other way, like, oh, so P is this, I guess, and didn't really work that way.
Yeah.
All right. Well, I'll stop recording now.
All right.
Okay.